Log on, tune in, find out. Another good idea from Cambridge.
And estimation, and our lecturer today is Eugene Demidenko from Dartmouth College, and you see the title of his lecture on the screen. Eugene, it's all yours, and we have 1 hour for the lecture.
First of all, thank you very much for organizing this workshop. I believe it is important to get together and discuss the problems we face when it comes to estimation, inference, and particularly designing and finding an optimal design. So, as you know, Dartmouth College is in New Hampshire. This is part of New England. So in New England, we say that if you don't like the weather, wait 30 minutes and the weather will change. So this is very much like here. So that is why it's, I believe, what's called New England by using weather conditions. My talk is simplified because we heard so much about properties and models and all kinds of types of models. So in this respect, it is easier for me, so I will skip some slides and don't be irritated if you see and hear from me again what you heard before. Okay, so the outline, I will start with the essence of mixed models, and I will skip all these computational issues and dog baits and made a nice introduction in what we can do using programming and using standard software such as R, SAS, S+, State, etc. So next I will try to convince you that mixed model is a frequent encounter when it comes to statistical analysis and when you see clusters using the Simpson's paradox. Then I will show you the table of models, different types of mixed models. I call it mixed models nomenclature. And also I will talk about overview of estimation procedures. Then I will talk about hypothesis testing, why mixed models, the fundamental question of hypothesis testing of variance-covariance matrix of random effects. I will introduce coefficient of determination for random effects. I will talk about criterion of existence, unbiasedness, non-iterative estimation, balanced data, generalized mixed models, and I will talk about very specific GLMM, such as binary models with random intercept, including probit and logit. I will briefly show you how Laplace approximation works, and make few comments about deterministic and stochastic asymptotics when it comes to model investigation, and of course challenges of optimal design, because the reason I'm here, you are interested in optimal design, so how mixed model is related to optimal design. Okay, we have a long program, so let's start quickly. First of all, you have to remember that mixed model is about the variance. Mixed model tries to explain the excessive variance cluster data brings in your model. So it's nothing to do with modeling of the mean. We're talking about modeling of the variance. And this is a very simple linear regression. If you specify variance of eta in this way, you can say this is a mixed model, and gamma is the variance of the random effect. Consequently, if you're talking about linear model and you try to use least squares for linear model, least squares gives you unbiased estimation. So don't forget that. So least squares may have less efficiency, but it is at least unbiased for a linear model. For a nonlinear model, the situation is different. Mixed model is used for multi-level, for cluster data. So if you have if you see clusters, if you are believe that some data come from the same population, so then your mixed model may be a good way to go. And particularly mixed model is used in longitudinal analysis, where, for example, you are talking about treatment and you have follow-up patients, and of course different patients have different baseline at the time zero, so you basically have a linear model with random intercepts. So this is a cluster model where one individual is one cluster, and you have longitudinal measurements of his or her blood pressure, whatever characteristic is important. Okay, Simpson's paradox. Good for men, good for women, bad for people. How is it possible? This is how. Look, let's say this is X, this is Y. So you concentrate on men, you ask only men about association of X with Y. I don't reveal this X and Y, but you can imagine the situation is possible when in the man population you have a positive relationship. For women, you have also positive relationship. But if you don't pay attention to the gender of your population, this kind of relationship you get. Good for men, good for women, bad for people. The Simpsons paradox. And you can find the description of this paradox in Wikipedia, everywhere on the web. So nobody mentions that this paradox is about the beginning of mixed model. This is about the mixed model. Why? So to make this claim more clear, I bring your attention to a more interesting example. This example is from my book. So this is the price of what are you laughing at? This price of a product, and this is the sales, and you are CEO of a big marketing company, and you want to know how price is related to sales. Does it mean that when you increase price, sales go down simply because people don't buy much? Yes, if you take this data, and let's consider this a television set. So each point is a television set. So if you look at the relationship, yes, increasing the price means decreasing the sales, so people buy less, right? Everything is fine. You can go ahead, make decisions. Now, you hire a new student who got statistics degree, and he looks at the data and says, wait a minute, this is one type of television set. This is another type of television set. So these are television sets with low price, high sell volumes, like television sets you put in the kitchen, right? They have low price, small, huge sales. Those are HD television sets. So this is one, let's say 65 monitor inch television set. This is 63, etc. So the price is high, the volumes is low. So if you consider these points as a part of your cluster, and you connect these points, what is the relationship? The relationship is positive. And if you want to come up with a new television set, and you want to predict the sale of these, like for example, this is a television set with new characteristics, and you want to predict the sale volume based on price 15, this is your number, right? And of course, in this case, considering each observation as a cluster from a specific television set specification, the price is positive. Do you see the correlation of this graph with Simpson's paradox? This is the same story. The only difference is that I have only two clusters, and here I have many clusters. The Simpson's paradox is the origin of mixed model. So every time you have data, please consider if your data come from different clusters. And if you don't account for clusters, you may make a huge mistake. Now, what kind of models we have? Basically, we have three types of models: linear, generalized, mixed model, and nonlinear. So in the linear model, if I must, what is the simplest linear model you can imagine of? Meta-analysis model. Who knows what meta-analysis model is? Raise your hand. Only a few people. This is actually very simple. So what meta-analysis model is about, you have different, let's say, clinical trials, and like a specific operation, how it affects survival, right? And you have 30 trials around the world. But you want to know the final answer. You combine the studies. Of course, you can take the average survival, right? But the issue is that each clinical trial has different sample size. So each clinical trial has its error. So you have to weight, right? So you may use weighted least squares, but also you may account for the fact that studies may be heterogeneous. So you introduce random effect. So meta-analysis model is the simplest mixed model, and every time I devise something like in terms of estimation, I start with mixed model. This is my meta-analysis model. This is my toy example. So I tune up my technique and I look at meta-analysis model, how it works, because in many cases I may come up with analytic solution. Random intercept model, several speakers use this model. This is the second on the list in terms of simplicity. Growth curve models where coefficients of linear regressions are random and explained by other covariates or explanatory variables. So you have hierarchical linear model. This model is called growth curve model. In this family of growth curve models, rectangular means you have the same number of observations per cluster. So you basically have a rectangular model. And balanced growth curve model when you have all covariates are the same. And Ryan actually used this model in his talk when all you have balanced model, rectangular model, and all xz's in notation of Doug Bates are the same. Finally, general linear mixed model, and this is, I call it linear mixed model with linear covariance structure, where it reminds our variance components model, but your matrices at the random effects are general, so you don't specify these matrices. Remember, in linear mixed model, those matrices are Z sub I, Z sub I prime, so transpose, right, in notation of Doug Bates. So if you don't specify these matrices, you get linear mixed model with linear covariance structure. And believe it or not, it is sometimes it's easy in terms of mathematics. It's easier to work with these kind of models and then translate the results from models with linear covariance structure to specific models such as growth curve model or random intercept model or general mixed model. Now let's talk about generalized mixed model. So we have several types. Of course, logistic regression is the most popular when it comes to analysis of binary data. Probit regression, where the link is a CDF of normal distribution. Poisson regression, and beta binomial model, which is a specific, very special class of models to deal with binomial data. Nonlinear mixed models. The first nonlinear marginal model, I call it marginal model because sometimes it is possible to treat, like imagine you have an exponential model. An exponential model has nonlinear parameters, but you believe only the coefficient which defines the starting point, so the intercept in nonlinear model is random. So then you end up with a nonlinear model, but covariance structure doesn't contain any nonlinear parts, so you don't need to have integration. So if you don't have to have integration and y is continuous, you use fixed matrix random effect nonlinear model. Then varied matrix of random effect model, when your covariance structure depends on parameters that may be related to the marginal mean. So you have marginal mean, covariance structure. If they are separated, this is type fixed matrix effect model. If they share parameters, it is called varied matrix of random effect. And you can combine these models and you talk about type 1, 2, 3 nonlinear mixed effect models. And finally, a general nonlinear mixed effect model where you have a general structure and which requires integration. And I use asterisk to show that for this type of model, you may come up with unbiased estimation and no integration is required. So you can use, and I will show you how to do this, you can use estimation methods with no integration. So again, brief overview of estimation procedures. Of course, you can use maximum likelihood, which requires integration. But remember that when to make the decision, you always, when do modeling, you always try to make your model adequate. On the other hand, make this model workable, so you don't have to have 1 million random effects and do nonlinear mixed effect model using maximum likelihood. As Doug Bates told us, when number of random effects is huge, you can't integrate. So integrals are very hard to evaluate when the dimension is high. So usually we can do 1, 2, 3 maximum. So for linear models, we have several techniques such as method of moments and Q estimation for variance covariance matrix, D matrix, and you can avoid basically maximum likelihood. For nonlinear mixed model and for GLMM, you can use Laplace approximation, and it brings you to the class of estimation called pseudo likelihood approach or penalized likelihood, and that was covered in the previous lecture. And I pay a special attention to model-specific integral estimation, like logistic probability or Poisson regression with random effects. In my view, and this is my philosophy, that each link has its own unique properties. For example, probit model with normally distributed random effect is very different from logit model with normally distributed random effects. While probit model can be reduced to using closed form solution. For example, marginal mean can be computed in closed form. For logistic regression, it cannot be done. The same for Poisson model. Poisson model is between linear model and probit model, so it is the simplest on the list of nonlinear models. I will show you why. Okay, so in many when it comes to linear models analysis, a fundamental question is usually overlooked, and the fundamental question is why I have a mixed model. I need to prove in every single linear mixed effect model that my variance covariance matrix here is positive definite. Maybe I'm trying to unlock an open door, so we have to test this hypothesis, and right now we don't have much technique to do this. So what I suggest is to use f-test, and this f-test is a generalization of variance components test you can find in books by Searle, Rao, Cleffe, and Curry. So this is kind of test you can find in the book where they consider more simplified models. This is simple a generalization. So what you see here, SOLS is a residual sum of squares from ordinary least squares. So you basically take the model, you compute least squares, you forget about random effects. You got residual sum of squares. S-mean is an important quantity. It's a pivotal statistics, if you wish. So what you do, you free your random effects, and it means that you think of random effects as intercept terms. And if you, or free coefficients. So if you free them, you basically minimize this sum of squares. And this sum of squares appears again, again, and again when it comes to investigation of properties of linear mixed effect models. So it means, and it can be proved, that if you put d to infinity and you compute the residual sum of squares in your using generalized least squares, this kind of the limit you get. So you free b and you compute this minimum using dummy variable approach, for example, using simple least squares. And under now, this quantity right here has f distribution. So you simply compute this value and test the hypothesis that your random effects present in your model. And the formal definition is you create this huge matrix, so you combine all axes here, and your variance components matrices Z are on the diagonal. Yes?
What is the alternative here?
Likelihood ratio test.
What is the alternative? No. I mean the alternative. Is the alternative that D is positive definite? Or
Non-zero. So it means so at least one element is a non-zero.
but the alternative should be that it's positive definite.
No, because there is lots of matrices that are zero and positive definite. No, alternative, because then you create holes in your space.
So the alternative, or the
It's not a scalar. It's matrix. Remember.
No, but it's
No, the alternative must be so that you cover the entire space of non-negative definite matrices.
also the alternative is that it's non-negative definite and not zero.
Right.
Okay, I see. Okay.
I tried to answer what the alternative criteria are. Log likelihood ratio test, Wald test. But the problem with all these tests, they're asymptotic. This is exact test. So this test gives you the exact size. Okay. We know coefficient of determination for linear model, how to specify, how to deliver the message about the strength of your random effects. Okay, you get 0.31, another got 15.2. It doesn't mean that 15.2 greater than 0.31. You can't compare because you have different scale on your dependent variable. So you have to come up with a measure which delivers the message that your random effects are strong or weak. So when it comes to coefficient of determination for linear model, you simply use weighted least squares, and you use matrices V, and matrix V is basically the variance covariance matrix of your dependent variable, and this coefficient tells you how X is related, how strong Y can be explained by X, in the same manner we use in standard linear regression. but it doesn't tell you how strong random effects are. To find how strong the random effects are, I suggest to use this coefficient. And in this coefficient, you measure the strength of your random effects on the scale of maximum value of the random effect. The maximum value of the random effect, so actually there is no random effect if you simply assume that BI's are fixed parameters. So then your sum of squares is minimum. So I suggest to use this interpretation where SMM is residual sum of squares, which comes from your estimation procedure. So this is residual sum of squares. You subtract the minimum value sum of squares it may have, and this is when BI's are not random and you set them free. And this is the definition I showed you before. And in the denominator, you have the difference between least squares, which assumes no random effect, right? You forget about random effect, minus S mean. So using this coefficient, you can say, using different y's, that this model has more random effects, this model has less random effects. And good thing that it's this coefficient from 0 and 1, and you can use this coefficient in the way you use the coefficient of determination for linear regression. So it is from 0, 1, when r squared a random effect is 1, you basically have d is infinity. When r squared random effect is 0, d is 0. And basically, r squared random effect is the proportion of the variance reduction due to random effects. This is how you judge about the presence of the random effect in your linear model. Okay, another point is always overlooked is, do we have criteria for existence of maximum likelihood? So everybody jumps into runs NLME without actually testing. Maybe my model is so bad that my data, or in case of my data, there is no maximum likelihood. And usually what happens that your program crashes and you have no idea why. So it is remarkable that the same, remember S mean, right? So the criterion is simple like that. If S mean is greater than 0, then maximum likelihood estimate exists for linear mixed effect model. So again, this guy appears again and again when it comes to linear mixed effect model analysis. Like, consider this model. This model is wrong. So in this case, I'm greedy and I want to estimate fixed intercept, and I introduced random effect, and they are right here, right? You cannot estimate simultaneously a random effect, cluster-specific random effect, and cluster-specific intercept if you combine them in one model. And you can prove that for this model, S mean is 0. What happens when S mean is 0 is that your d goes to infinity. Remember, S mean is when BI's are setting free, so it means d goes to infinity. And when d goes to infinity in terms of algebra, the same happens when you try to maximize likelihood. You have divergence in your NLME or whatever, so your program will crash. So before jumping into estimation, please take a look at your model, use this criterion. It is very helpful when, yes?
Can you be a bit more explicit about why S-min would be 0 in that case? I mean, if there's some variation in the Yij within a given I, it can't be accounted for by gamma.
Here's the explanation. The best random effect will be 0, yes, because everything will go to intercept term.
Yes.
So this guy becomes 0, so it means D is 0, and when D is 0, terrible things happen.
Well, not necessarily. But under certain methods that I'm looking at. So D goes to 0, but it still doesn't make S-min 0.
That's right, but maximum likelihood goes to infinity.
Yes. Well, not.
Yeah, maximum likelihood goes to infinity. So you get
There's the other
sensible estimates, but maximum likelihood goes to infinity, and computer can't work with infinities.
The question is why S min is 0.
Yeah.
I think it's a
Ah,
difference between SOLS and S means that goes to 0.
Okay, I can go back to the definition. Okay. Yeah, right here. So what happens that you have intercept term here and intercept term. So you cannot distinguish between these two.
I accept that. So set all the bi's equal to 0. You're still saying that you can reduce the residual sum of squares to 0 by only the beta, which is not necessarily true in that model.
I need to
Difference between OLS goes to 0.
perhaps I need to put this guy to 0. So this kind of model, then you have zeros. I may overstate this.
You have to introduce the second index to either alpha or b. You have an extra index with y, j. So you have y sub I sub j, and therefore your sum of squares is not 0. You see, in your definition of S minimum, you have only one subscript.
Right.
That's why it can be 0.
Right.
You have an extra subscript, j, so you have extra observation. So in general, if j is not
Maybe I screw up here.
S minimum will not be 0.
Yeah, I see the point. Maybe I screw up, but
So it's something with notation.
right. Okay, so the same. It is also important to have the criterion on positive definiteness. I was asked about this criterion. So this is not a statistical criterion. This is a computational criterion. So basically, what you see here, this is a existence theorem. So why this is true? It's simply you compute the likelihood on the boundary, and you show that the derivative points to the inner point of the boundary for your positive definite matrix for D. So, and if you write down the derivative, and of course you should derivate with respect to matrix, this kind of matrix you get. So if this derivative is positive, so you have a maximum of likelihood outside of the non-negative matrices, and for one random effect you have very simple criterion by which you can judge that your maximum likelihood is positive. Okay, so once D is estimated and you have D hat, this you use generalized linear least squares estimated to compute beta hat. And it is important to, actually it's also another fact people overlook. If D hat, like in maximum likelihood or method of moments or mean Q, is estimated using, based on the symmetry, using symmetric functions, if you wish, then the distribution of beta hat is symmetric around beta true. So we can prove that this estimator is unbiased in finite samples. So this fact usually is overlooked. And since this estimator is unbiased, So the next question is how about efficiency? So this is an open problem for you. So basically we are talking a new Gauss-Markov theorem when covariance matrix is unknown and estimated. Can you prove Gauss-Markov theorem, which says that this estimator is the most efficient in class of all unbiased estimators, let's say assuming normality?
What is the estimate of D?
Either maximum likelihood or method of moments, or but it is a symmetric function. So now let's talk about non-iterative estimation of variances, including sigma squared.
But can you prove that there existence of such an estimate? Because you can assume that when
No,
it's
it is.
symmetric,
It's
but
right.
can you build a symmetric estimator?
No,
for
it
D?
it exists. Maximum likelihood belongs to this class. If you plug in the MLE for D hat here, this D hat is symmetric matrix. You can prove it. And also, if you use mean Q, it's also symmetric matrix. So yeah.
But maximum likelihood will, with finite probability for finite n, always be on the boundary for this matrix D. So it's not symmetric.
Why on the boundary?
Because it should be positive, definite. Positive definite, and we
So
know
it
it's
is-
finite probability.
It is inside. It's not on the boundary. It's inside
with
this
some
scope.
probability. But with some probability, it should be on bound. Because of its known phenomenon. So maximum likelihood leads very often, if you do not put any constraint, to non-positive definite matrices. And it means that with finite probability, you are sitting on boundary. And
But
therefore,
but-
there are a lot of problems with
But
that.
it's not. I don't see a problem because if it's on the boundary, so D is let's say 0. If you plug in 0, so it means ordinary squares, and it's unbiased and it is efficient. So I don't
It's
see.
not all elements, it's only part of it.
It's a matter of future investigation. Now we can't solve the problem right here.
I agree with this.
So now let me talk about several non-iterative estimation of the variances. So this is alternative to maximum likelihood. So first of all, we can generalize mean Q estimation. Mean Q was popularized by Rao and Clef and their book. So basically, among all unbiased estimators, we are looking estimators with minimum norm. So those estimators are quadratic functions of data. So that is why I call it symmetric. Method of moments, you simply compute empirical moment matrix for D. You compute the expected value, and you solve the equation for D. And it turns out that you end up with a linear equation. The equation is a very messy, very heavy matrix, heavy equation, but you can solve using Kronecker products. And finally, you can use variance least squares, and particularly you can use unbiased version of variance least squares. Let me talk about mean Q for sigma squared. So basically, you say that I'm looking for sigma squared using this quadratic form, where A is a matrix, and this is a huge matrix. Remember, Y is a long vector of my data, so I combine all observations from different clusters. And among all these A's, I want to find A such that this trace is minimum. And also I want to make this estimate unbiased, so this is unbiasedness condition. So, and since the variance of quadratic form can be expressed in closed form, you end up with a quadratic minimization of quadratic function expressed in terms of matrices under these two conditions. If you do your calculations, this is the variance for comes from mean Q estimated with no maximum likelihood. And this variance, remember, this estimation of the variance is unbiased, and matrix W appears as it appears in my S mean right here. More than that, you can prove that mean Q is equal, the variance of mean Q is equal to the variance of restricted maximum likelihood for balanced random intercept model. So this is the connection between why we use restricted maximum likelihood, because it is actually mean Q estimator for balanced model. Now, how to compute a method of moments for D, and I skipped mean Q for D because the equations are huge, but it's possible to solve this quadratic problem with linear restrictions. So method of moments. So what you see here is your estimate of your random effect. And of course, if random effect, if you take the sum of random effect and you divide by n, it is a sort of approximation of D. So what you do, you simply take the expected value of this matrix and you equate to the empirical value. This can be shown that this expected value can be expressed as a linear function of D with some matrices in front of D and to the left and to the right of D. So you use vector notation and you express D as a linear function of matrix at right. So this is the method of moments for D. This method of moments doesn't give you the unbiased, in some cases unbiased matrix D hat, but using some techniques you can make it unbiased. And it is possible to show that this estimate is actually boils down to estimate of variance components in simpler models, and you can look these estimates in the book by Searle. So variance least squares. What is variance least squares? You get residuals using ordinary least squares, and if you compute this matrix should look like the variance covariance matrix in cluster I, and you simply compute D so that using sigma squared either from mean Q or simply finding sigma squared, so that the differences between empirical version of matrix V and theoretical version are as close as possible, and you get estimates for sigma squared and D. D star is the product of sigma squared and D. So how to use these estimates? We know that in some cases maximum likelihood breaks down, so you can use this estimate either as starting points, or you can use these estimates as alternative to maximum likelihood when maximum likelihood doesn't work. And remember, for example, for linear least squares, I never used a normal assumption here. So you can, if you believe that your data is not normal, you can use this estimate.
Is it okay to interrupt you with question?
Absolutely.
So, this is the least square method for this variance covariance matrix. And so if you do really maximum likelihood method for in the same setting, in normal setting, then you will also have actually the formula which actually leads to the same estimator but only weighted with variances of these variances. So you propose to use unweighted least square. Instead, maximum likelihood leads to weighted least squares.
Absolutely agree. Absolutely agree.
Just first steps.
But remember, in maximum likelihood, your weights depends on D So it becomes very messy. So you have to iterate, and iterations may go to nowhere.
No, it's converged to maximum likelihood.
Yes, but maximum likelihood may diverge because you have overspecified model, because blah blah blah. Here you get D explicitly with no problem of convergency, with no problems of
It's the same
continuity.
kind of blah blah here, but just unweighted blah blah blah.
Agree.
Okay, can I interrupt with a second question? Back on the next slide.
Uh-huh.
One of the first things you showed us was, first, a preliminary question. I assume the beta hat OLS and the EIs are from simple OLS regression just on the X's. Is that correct?
Right.
If you're in a situation like you showed at the start of the Simpson's paradox, where the OLS can really go awry, is that also going to give you very bad estimates here?
I didn't try that. That's a good question. Let me know.
You may get very the residual.
Right, I
may
see
not
your-
look at all. the
Right.
way they really
I
should.
see your point. My residuals are wrong in the first place, and I'm trying to improve things using wrong start. I don't know. You can publish a paper. Balanced data model. I encourage you to make your data balanced. When data are balanced, you have less problems, and basically when data are balanced, for example, in random effect model, you don't deal with D when it comes to computation of betas. So betas are D independent. And also for balanced rectangular linear growth curve model, when Z's are explained through this part when Q is a set of vectors, then in this symbol is Kronecker product. So you also have independence of beta hat from D. So this kind of balanced data are always good because it gives you very stable results, and it gives you a good opportunity to do your analytics. Balanced models are good when you have analytical tools and you can prove or see what kind of results you have for like optimal designs using balanced models. And that was demonstrated in previous talks. So a balanced model is a good start when it comes to investigation of properties of optimal designs. Okay, generalized linear mixed model. This is a general setting, so we start with exponential family of distributions, and I simply want to show that this kind of integral you are facing here. So this is an integral, and this function and the exponential function is not quadratic, so you have to do numerical integrations, and you can do numerical integrations, but the number of random effects is 1, 2, 3, maybe 4, but not more than that. Integration is hard when the dimension is higher. Yes?
It's not the number of random effects. It's the structure within the random effects. So in your case, you have one grouping factor. You're saying yi equals, etc. And for that, it's the dimension of the random effects within each cluster. So if you just had a random intercept model, that integral is expressed as a product of scalar integrals.
No, I agree, but my definition of dimension of random effects is dimension of metric Z.
Okay.
Metric
I thought you were
Z.
talking about the number of
No.
groups.
So this where we need to look for alternative to maximum likelihood. I mean, when number of random effects is huge, and I faced this problem when I applied mixed models for imaging. Then if you have imaging, you have like each image is 256 by 256. You end up with random effects 256 squared. So how can you integrate this? Forget it. So you have to come up with approximate methods and perhaps specifically to each model. Okay, we need to move faster. So this is binary regression with random intercept. This is very nice introduction to mixed models when it comes to binary data. So basically you have the same predictor, so as in linear model, and mu is inverse link, so I call it probability function with these properties. So this is how you model probability of Yij. When mu is a logit, you have logistic regression. When mu is a CDF normal, you have probit regression. My point is that in many cases, the authors consider GLMM in general setting. My point is that when you take a specific family, you can find specific estimation procedures which are much more efficient than even maximum likelihood. This is my point. And people don't pay attention to these special classes. And I claim that each class of GLMM has, or GLM, can be treated separately, and a specific solution to GLMM estimation can be found within each type of models. So, and to demonstrate this, I simply look, if you have probit model, if you have normal random effect, you can find marginal model simply using this nice relationship between exponential, between the expected value of CDF, and you see that the marginal model is attenuated. So this is the demonstration of attenuation, and this is the demonstration of the differences between individual probabilities and marginal probabilities. So this is the marginal probability which actually can be computed simply by averaging curves right here. So remember that marginal probability flattens out your model when probit regression, even logit regression, has a random effect. So don't forget about interpretations between marginal model and individual model. I remind you Laplace approximation. A Laplace approximation works amazingly well when a matrix, when a function h is about quadratic. So you approximate by quadratic function, and then you end up with this approximation. And this approximation is the basis of many estimation procedures for GLMM and nonlinear mixed effect models. Now let me briefly talk about GE for mixed model. And my this is a simple theorem about how to solve, how to estimate the model using the fact about score estimation, or we call it estimation using estimating equation approach. But the problem is that when you apply this estimating equation approach to GLMM, you end up with the method with no model. So my point is that GE is a method of estimation of unknown model. And I call it, people call it working correlations matrix. I call it non-working correlation matrix, because you never can find a good correlation matrix when you use GE, because it doesn't exist. So the assumption in GE is assumption that you have marginal model of fixed part plus random effect, and it doesn't work when we have binary data. You cannot represent binary data having expected value plus a random term. It is all together, and you cannot separate covariance matrix from the expected marginal mean. And fundamental problems with GE, impossible to generate data basically using GE. So I encourage you to use mixed model and use GE only as a starting point for maximum likelihood. A nonlinear mixed model, again, I simply use notations to show you that the integral appears here and the number, the integral dimension equals to dimension of random effects. So I show you an example how logistic regression with random intercepts may be reduced to conditional regression. This reduction reminds the reduction we use in partial likelihood when it comes to survival model. Cox proportional survival model uses the same technique, conditioning on sufficient statistics. And if you do this conditioning, you end up with this likelihood function, which contains no integrals and very, very close to real maximum likelihood. The same you can do with Poisson regression, and what is important, again, you can compute marginal. You see, the only difference is that you get this coefficient. So this coefficient comes from random effect, and the only difference between mixed effect Poisson model and this model is you spoil only the intercept and you leave your coefficients untouched. So you can use Poisson regression with random intercept, just use traditional ordinary Poisson regression and you get consistent estimates, and the estimates will be just fine. To demonstrate how it works, I use and this result is computed using analytical tools. No simulations are involved. So right here you have Poisson regression with random intercept. This is maximum likelihood. This is exact GE, and some people in previous talks used exact GE to compute the.
Can you tell us what the axes are?
Axis here.
Yeah.
This is a standard error of cluster-specific intercept, and this is relative standard error of the slope. So this is maximum likelihood. So this is exact GE. When you use, you compute covariance matrix for Poisson regression using analytical techniques. This is a fixed intercept, so you simply assume that your intercept are fixed values. You use like dummy variable approach. Right here is GE, like regular GE, assuming equal correlation structure, and you see GE is terrible. And this is ordinary Poisson regression, where you don't assume any randomness. So in this case, exact GE works just well. You simply need to, instead of working correlation structure, which comes from nowhere, you simply compute exact GE, and it is possible for Poisson regression. A few words about differences between deterministic and stochastic asymptotics. So stochastic approach assume that x's are conditional, and that means that your theory simplifies dramatically. So you simply use estimating equation approach, and you don't spend much time on proving all this lengthy result about consistency and asymptotic normality. It's simply this theory can be derived using IID case. Remember, in mixed models, we have two types of asymptotics. We may increase number of clusters to infinity. You can increase number of the observations within the cluster, and these asymptotics are different. So don't always remember that we can go different directions. And of course, when you compute optimal designs, and Vlad will talk about this, how we can go in optimal designs using either increasing number of clusters or number of patients, if you wish, or increasing the follow-up period for each patient. And we have a trade-off, and it's a great optimal design problem to solve in the framework of mixed models. And finally, I can't resist not to advertise my book. So I'm working on the second edition. Take a look at my web page home.
Any questions to Eugene? All questions have been asked during the
Right,
talk.
right.
In these cases, usually chair asks something.
So I'm still waiting for the audience.
Will there be any optimal design in your book?
No, no. I leave it for you.
All right. If there are no more questions, thank you.